from what I got from it is that the human brain is so complex that you have to kind of approach it with this very like structured hypothesis already.
Yeah.
And so when
Yeah.
people end up finding things that they were kind of looking for, we
Yeah.
shouldn't take that, as seriously as if they had just been studying it kind of objectively.
Well,
Or
you can't, I
wrong
don't
word.
think you really can study this stuff objectively. I mean, there are some people who take, again, a sort of super data-driven approach where they say, let's focus on the technology and try to record as many neurons as we can. Let's just try to record everything that the brain is doing. And sometimes like shrink down to very simple model animals, like the nematode worm that has only 302 neurons, or
I've heard about this stuff, like the C. elegans.
C. elegans, exactly. Whoops,
was that you? Yeah,
that was me. Sorry.
So like I've seen things like that, or connectomics, I think they call it,
Yes.
where you can actually
Yeah.
map out every single individual neuron and you can watch the kind of firings.
Where they say, let's forget even having a frame at all for thinking about what the brain might be doing. Let's not have these sort of hypothesis-driven experiments. Let's just get as much data as we can. And they've made a lot of progress with this. But often there, you just end up drowning in data. And so then they sort of say, all right, we'll put the responsibility for interpreting this on, the next generation of scientists. We'll get the data, then we'll have other people figure out what to do with it. And some of it is, I think that some of the best work I've seen in this area probably comes from Mitya Choklovsky's group. Though Sebastian Sung has also done really fantastic work here. But for instance, there are hypotheses on the way, for instance, the flies perceive motion.
Okay.
Different possible simple circuits for how the fly's eye can figure out, am I flying to the left or to the right, or is this object looming at me? When you go to swat a fly and it just flies away really quickly, how can it do that motion computation? The theories themselves were proposed about 60 years ago. They were some of the first neural computation models put out there.
Were these based on observations, or were they based on just kind of
These were just based on
hypotheses?
sitting down and thinking like, all right, if I were going to design a circuit out of neurons to detect motion, what would be the different ways that I could do it? And one of the earliest ideas was what's called the Reichardt detector, which is basically a very simple circuit where you have sort of two input neurons, and then you have two processing neurons, and there's a time delay going from one to the other. So that if you have some object moving from left to right, then first the neuron on the left will detect it, then the neuron on the right will detect it. And if you have a time delay going from the neuron on the left, then the signals will be coincident, and you have a coincidence detector, and the moving from left to right neuron will go off if it's activated in that order, and then you have a similar time delay going in the opposite direction. And if you spend 10 minutes thinking about this, you could probably come up with something similar. If I guess I've spoiled it for you, but if I were to put you in a room with this problem and not tell you what the solution was, it's probably what you would come up with also. So it takes about 10 minutes to come up with a theory. It's taken about 60 years to validate it as true or false.
Oh, wow. Have they done that now? Is that
So
pretty accurate?
I'm not completely up on the state of the field, but a few years ago at least saw a very good talk from Mitya where they went in and did very detailed connectomics of the circuitry of the fly retina and were able to find a certain set of neurons that seemed to have a structure suggestive of Reichardt detectors. So it looked at the anatomical level like it did exist. So this is a good case of hypothesis-driven neuroscience combining with the data-driven neuroscience. I think that's a really excellent example of it.
Yeah, it's funny. As soon as you mention it in that way, it seems so obvious. Where it's like, oh, of course, of course, that's what you would do if you were trying to detect the movement of something left to right.
Like I said, it's you spend 10 minutes thinking about it, and you could come up with this.
And so simple as well. You only have two pieces basically.
Yeah.